first of all, I would like to thank a lot to the ITU organization for organizing this great challenge, the ITU AI ML challenge in 5G. And particularly to the ITU Secretariat, which in particular to Reinhard, Vishnu and Thomas, which gave us a great support and made an excellent organization work. So my presentation today will be about the Graph Neural Networking Challenge 2020, that is in the ITU document about the problem statement is the reference number 14. So you can check more details also in this document. And first of all, I would like to introduce myself, although Reinhard also introduced me. So I'm a researcher at the Barcelona Neural Networking Center at Universitat Politècnica of Catalonia. So all this challenge was organized by all my group, the team of researchers where I work. So first
Jose,
of all,
maybe if I can, Jose, if I can say maybe a couple of words, I forgot to mention it. So if we have about 30, 40 minutes for your presentation, and then we have until the rest of the hour, we have available for question and answers. So participants are welcome to put their questions in the chat, and then we will just hand them the floor later and have them ask the questions directly. But perhaps maybe some of you who are listening can already put in some questions. And just to answer one question that I see on the chat is, yes, we are recording the webinar. So everything is being recorded, and then we will put it on the website afterwards. Okay, back to you, Jose.
Okay, so thank you very much. So I will make the presentation making a brief introduction on graph neural networks. Then I will explain some details of the challenge. So at the end, I will respond to all the questions that you can either do on the chat or online. So first of all, I would like to introduce graph neural networks to those that you probably don't know this machine learning technique. So graph neural networks is basically a novel neural network family that is specifically designed to learn from data that is structured as graphs. So these kind of neural network architectures have been recently promoted and popularized by some people of Google DeepMind, including other authors also from the academia, from the artificial intelligence field. And they have been already extensively used in other fields where the data is fundamentally represented in the form of graphs. So this is the case, for example, of chemistry, where we have data such as molecules, where that are represented as graphs with some atoms and chemical bonds. So we could see many important and relevant applications, for example, in this field. So to give you an overview about the main neural network architectures, I would like to highlight these 4 types that you can see at the left column of this table. So the first one and the most primary or basic one are the fully connected neural networks. So these neural network architectures are particularly designed to process and exploit information that do not have any particular structure. So we have arbitrary order or arrangement. And they can be used, for example, to address problems of generic classification or non-linear regression in general. Then we have other more specific types like convolutional neural networks that are especially designed to process data that is arranged spatially. And this is the case, for example, of images or video. And these kind of neural networks have many successful applications, for example, in the computer vision field. And then a third type are recurrent neural networks. So these architectures are particularly tailored to learn and understand data that is sequentially structured. An example of this is, for example, text and voice. So they had really good applications, for example, for text processing or voice recognition. And finally, I would like to present graph neural networks. So these neural network architectures are particularly designed to understand, learn, and model information that is relational. And the main example of this kind of information are graphs, where we have some elements that are related between them. For example, molecules, maps in logistics, or networks, including either computer networks or social networks, as an example. So just to give you an overview of the current status of graph neural networks, I made a quick search on Google Trends with the graph neural networks keyword. And as you can see, there is here there is a graph with evolution of the topic over the last few years. So graph neural networks were proposed around 2008 by Franco Scarselli and other authors from the University of Siena in the paper called the Graph Neural Network Model. But then in 2018, some people from Google DeepMind presented a position paper on graph neural networks where they highlighted the applications that they could have to many different fields. And from this date, we can see that there is an important search on this topic. So we can state that today, graph neural networks are a hot topic in the field of artificial intelligence. And particularly, they have many applications on different fields that rely on graphs. Like this is the case, for example, of chemistry, like for example, for data that, from molecules, for biology, for example, for proteins, physics, logistics, for example, when you have some information arranged in a map, social networks, and the case of computer networks also. So currently, we are witnessing large efforts that are being devoted to develop the theoretical foundations of GNN. And we are also experiencing some interest from the networking community that is starting to investigate also its potential applications. So at the bottom of this slide, you have a very relevant or very interesting reference where you can see some of the most relevant papers on GNN. So I recommend you also to check this link. So now I would like to introduce how can graph neural networks be applied to many different networking problems. So first of all, I would like to introduce you the concept of a digital twin. So basically, what is a digital twin? A digital twin is a mathematical representation of a physical or logical object. For example, in this image, you have an example of what would be a digital twin of a plane. So this would be a mathematical model that can be able to predict under different situations. It can simulate what would be the resulting situation. For example, if we apply some wind over the plane. So if we translate it to the networking field, this is a network model. And it can be used for a plethora of network optimization problems. And some examples would be, for example, to answer questions like, what will be the performance if I change the routing configuration or other configuration in my network? Or what can happen if there is a failure in a particular point of the network, like for example, on some links. So this digital twin or network model should answer the question that you can say in this slide. So given a network snapshot or a network configuration, is it able to predict the resulting performance that the network will have? So in the end, this digital twin is modeled by this box that you can see here, where we have some inputs that describe the current state of the network, like for example, including the traffic, the topology of the network, and all the configuration parameters of the network. And the output of this model would be to produce performance predictions, like for example, the delay, the jitter, or the loss that every flow in the network will experience. So how can we build a practical digital twin for networks? So networks are fundamentally represented as graphs. So for example, if we want to represent a network topology, the most natural way to represent this is in the form of a graph with some nodes and links. And then other fundamental components of networks, such as the routing configuration or the traffic that flows along nodes and links, are also fundamentally represented as graphs. So if we see to traditional neural network applications, we can state that they are not suited to learn from this information that is structured as graphs. Like for example, the types that I mentioned at the beginning of this presentation. So all the traditional approaches that use traditional neural networks, in the end, make feature engineering. So basically this means that they offer or they propose ad hoc solutions adapted to specific problems. And usually they do this to transform the problem in order to prevent learning graph structure information. So as a result, we can see that they provide limited performance and they are not applicable to complex real-world network scenarios. And what is more important is that they are not able to generalize to other networks that they did not see during the training. And to highlight the importance of this generalization capability that I have mentioned, I would like to briefly discuss how can we design practical machine learning solutions that can be deployable for networking use cases. So the idea is that if we want to produce this kind of solutions, we need a networking lab with controlled testbeds where we can produce different configurations and we can make some measurements to train the machine learning model, like for example, a neural network model. So once we train this with a large range or a large variety of configurations, we can have a final machine learning product. But then this product should be deployed in the customer network, in a real world network. And it should work well also in this network. So if we go to traditional machine learning solutions in general, we can see that the main problem to achieve deployability is that they are not able to generalize to other networks that were not seen during the training. So if we go to this particular case that I presented, when we train this solution in a networking lab, and then we want to deploy this in the customer's network, the machine learning product fails to operate in this customer network. And also, it's not often feasible to train the machine learning based solution directly on the customer network, since during training, it would require to implement costly network instrumentation in the network, in the customer's network. And also and this is more important, it may cause service disruption due to possible misconfiguration while the machine learning model is being trained. and also some alternative approaches such as transfer learning that try to address this issue are not applicable to this particular use case, since they need to be retrained also on the customer's network. So from this brief discussion, I would like to highlight that the importance of having machine learning models that are able to generalize to other networks that were not seen during the training. So in this context, graph neural networks were the only machine learning based technique that demonstrated capability to generalize to other networks. So we can train this in a networking lab and then deploy this in a real world network. And if we see to other alternatives that are not based on machine learning to build also these digital twins, and the main alternatives are first, network simulation that can produce very accurate predictions, but is computationally very expensive, which makes it difficult to operate the network in close to real time. And another approach is using analytical models that are mainly based on keying theory. But these kind of models are well known to be unable to model complex real-world scenarios with complex configurations and topologies. So the advantages that GNN provides with respect to all the state-of-the-art solutions, both based on machine learning and other traditional solutions, is that first, it is fast, so it provides a very low computational cost. Second, it provides very high accuracy comparable to network simulation. And third, which is probably the most important, is that it enables deployability in real world network scenarios. So this is possible thanks to the generalization capability to other networks. So this is unlike to other machine learning based solutions. So in the end, when we apply GNN to networking problems, it learns the underlying relationships between different network elements, like for example, nodes or links that are represented in the form of graphs. And this, as a result, enables to model accurately other networks that were not seen during this training phase. But here, there is, let's say, some limitations on standard graph neural network models, like, for example, those applied to chemistry, which are not directly applicable for computer networks. So in this sense, we need some custom graph neural network models that need to be adapted. Their neural network architecture has to be adapted to operate on different networking use cases. So from all this discussion, I would like to remark that GNN, or graph neural networks, can be seen as a generic toolbox that enables to build general or generic solutions for different networking use cases. So if we see, for example, to other fields where artificial intelligence had many successful applications, we can, for example, see to the computer vision field, where convolutional neural networks led to a very important breakthrough in applications and services. Like, for example, these neural networks enable to make some applications for facial recognition or self-driving cars as paradigmatic use cases. And the main reason behind this is that convolutional neural networks are well-suited neural network architectures to model information that is arranged spatially, and this is the case, for example, of images. So this enabled all these successful and important applications in the field of computer vision. So to make an analogy, I would like to remark that graph neural networks can have a similar impact in the computer vision in the computer networks field, similar or equivalent to what convolutional neural networks had in the field of computer vision, just to understand the relevance of this neural network architecture. And now, once I have done this introduction on graph neural networks, I would like to present the graph neural networking challenge and some details about this challenge that we organized as part of the ITU in the ITU challenge. So the problem that we propose here is to build basically this box or this digital twin for networks. So we ask for solutions based on neural networks where the input is a network topology, source destination traffic matrix, including all the traffic shared among all the source destination pairs, and the configuration of the input network. And this includes, on the first, the routing configuration, and second, the different queue scheduling policies on nodes. And particularly, we consider these queue scheduling policies that you can see in the slide. So we consider strict priority, weighted fair queuing, and deficit round robin. And finally, the output of this model, or the objective of this model, is to produce mean per packet delay predictions on each source destination flow of the network, given this input. So for this, we generated a data set with a network simulation tool that is well known, and it's called Omnet++, and this is a discrete event packet network simulator. So we produced thousands of simulation samples that include different topologies, routings, queue scheduling configurations, and traffic. And particularly for traffic, we included a very large range of different traffic intensities to include all the operational range of the network. So the input are topology, configuration, and traffic matrix, and the output labels are the per flow mean delay, which are the ones that your models need to predict. So continuing with the data set and focusing on the queue scheduling configurations, particularly all the nodes in our networks consider 3 different queues where 3 different traffic classes are directly associated. So these traffic classes have different quality of service priorities. We included in this data set 4 different scenarios regarding queue scheduling configurations. So each scenario is, or the data set contains 25% of samples of these 4 scenarios. So these 4 scenarios are ordered in level of complexity. So the first one considers that all the nodes in networks implement a weighted fair queuing policy. And this policy includes fixed weights on the different queues. So for the 3 queues, we consider different weights, but in all the nodes, we have the same weights. Then in scenario 2, we consider that all the nodes implement weighted fair queuing as well, but in this case, we have variable weights assigned to the different queues depending on the node. The third scenario considers that nodes can implement either strict priority, weighted fair queuing, or deficit round robin. And in the case of weighted fair queuing or deficit round robin, we include variable weights over the nodes in the network. And finally, scenario number 4 is similar to scenario number 3. So it considers these 3 queue scheduling policies, but also it defines a different traffic profile for the 3 traffic classes considered. So this is a little more complex to model. So in the end, we published some data sets for training and validation. So you can see all the details in this link, and they are packed in compressed files. And also we provide a Python API that enables to easily read and process all our data set. So you can see also at this link all the details about this API. So as a baseline to participate in this challenge, we provide RoundNet. So RoundNet is a graph neural network model particularly tailored for networking tasks. So this is the box that you can see here in the slide. And basically this model learns all the relationships between the network topology, the traffic and routing, and how all these elements affect to the resulting performance of the network. So for example, to predict the delay for all the flows of the network. So what we could see in the reference that is at the bottom of this slide, it can generalize well to unseen topologies, routing configurations, and traffic. So we provide an open source implementation in TensorFlow 2.1 that includes many details, and it is quite easy to follow the code. But the main limitation of this baseline model is that it was not designed to model the impact of different queue scheduling policies on nodes. So this is very important for this challenge, as the dataset contains samples with different queue scheduling policies. So regarding the evaluation of the challenge, we will provide at the end of the, the objective or the main objective for the evaluation is to test the generalization capabilities of the proposed neural network solutions. So we provide a training data set that includes samples simulated in 2 particular network topologies, and then we have a validation and test data set that includes samples simulated in 3rd topologies. So the test data set will be released at the end of the challenge around the 11th of September. And from this point, the evaluation phase for all the participants will start. So we will particularly evaluate the capability of the proposed neural network solutions to make good delay predictions over the test dataset. So to this end, the test dataset will be unlabeled, which means that it won't contain any performance measurements, including the delay measurements that your model needs to predict. And the participants have to label this dataset with their neural network models and send these labels in a CSV format to the organizers. So to score or to evaluate the solutions, we will use an objective score, which is the mean absolute percentage error. That is the formula that you can see here, that basically measures the relative error between the predictions made by the models and the results from our simulation tool. So the winning solution will be the one that achieves lower mean absolute percentage error. So I would like to give you some tips and guidelines to participate in this challenge. So the idea is that all of you are encouraged to update the baseline that we provide, so RoundNet, or also design your own neural network architectures. So particularly if you want to update RoundNet, we recommend to try to modify the neural network architecture that we provide now to model or to enable modeling different queue scheduling policies on nodes, since this is the main limitation of RoundNet for the data set that we provide for this challenge. And also we recommend making some traditional techniques of machine learning, such as hyperparameter tuning or normalization of all the data. So for this, we provide a very useful tutorial where you can execute or learn how to run RoundNet and modify essential parts of the code. So here at this link, you can check this. And just before wrap up, I would like to remark that this challenge was organized as part of the ITU AI ML in 5G challenge, as all of you already know. So this is the reference number 14 in the problem statement document. And I would like to thank again to all the ITU members for making all this possible, because I think it will be a very important challenge to make more visible the application of machine learning to networking. So the target audience for this particular challenge, and in general, I think for the ITU challenge, for all the problem statements, is not only people with background from networking, but also people from the artificial intelligence community. And at this point, just remind that graph neural network is a hot topic nowadays. So people from this community are also can be also interested to participate in the challenge. And just to recap, I would like to remark the main resources that we provide for this challenge. So first, we provide a baseline model, which is called RoundNet, including a tutorial on how to run and modify the code. Then we provide also an API to process all our data sets. And also, which is also very important for participants, is that we provide a mailing list where you can interact with other participants and with the organizers to ensure successful participation. So the main incentives for participants to participate in this challenge, I would say that first of all is that this is a very good opportunity to introduce yourself in the application of graph neural networks applied to computer networks, since this is a hot topic, and this is a topic that will have a great impact in the next few years. So this is the first competition in the world regarding graph neural networks applied to computer networks. Also, this will give you access to the global round of the ITU challenge, where top candidates particularly will be considered by the ITU judging committee. And for the winners, they will have the opportunity to make a presentation at the final conference of this great ITU initiative, including also some awards. So you can see more details, particularly about this global round, at the link that I provide here. And regarding particularly this challenge, we plan to generate certificates of appreciation for the top 3 teams, and also they will be recognized in the challenge website. So we will publish a ranking in our website. Sorry. So also we will give the opportunity to make presentations of these winning solutions at the big demo workshop that which be co-located with ACM Connect also at the end of the year. And finally, we also offer the possibility for those participants that are interested to publish a paper which can be co-authored with all the challenge organizers, and we can tell about how was the experience participating in this challenge and give some details about the proposed winning solutions. So I would like to give some credit to all the people that organized particularly this problem statement, that we are these 8 people that you can see here in the slide, and we are all from the Barcelona Neural Networking Center. And finally, I would like to remark the timeline or the main dates about this problem statement. So you can see all the details at this link that I display here. And first of all, I would like to say, I think you already know, but the registration is now open to all participants. So you can participate in teams of up to 4 members. The challenge duration will be around 5 months from May 22nd that started this challenge to October 21st. So the main date now is the registration deadline that is fixed to June 30th. So you need to register to make the registration before this date. And then we will have an evaluation phase that will start on September 11th, and it will take 15 days approximately. And finally, after a compliance check to check that all the winning solutions comply with the rules of the challenge, we will announce the top 3 candidates in October 21st. So these winners will access to the global round of the ITU challenge, and they will be considered for the final awards and also to make the presentation in the final conference that will be at the end of the year, around November or December of this year. So here you can see also the registration link at ITU. So I provide here some links. And also this is very important to ensure or to guarantee successful participation in the challenge. We have a Slack channel where you can interact with the organizers and among you also. So finally, to wrap up, I would like to invite you and to encourage you to attend also the next presentation about a problem statement, particularly problem statement number 12, which is called ML5G Phi. I think it's related to wireless networks. And a member of the Federal do Pará University at Brazil will present this on the 26th of June. So yeah, that's all. So thank you for your attention, and please do not hesitate if you have any questions or comments about the challenge.
Okay, thanks very much, Jose, for this crisp presentation. Let me now go to the Q&A part, and let me introduce one of the colleagues which have been instrumental in putting this together. This is Vishnu Ram. He's an independent researcher, and he, together with Thomas Basicolo, have been really key people in putting together the challenge. So Vishnu has also been engaged very much. He was a key person in the ITU effort that's called Machine Learning in 5G Networks, or Machine Learning in 5G and Future Networks. So welcome, Vishnu. Vishnu joining from India. So I'll hand over to you, Vishnu, for the moderation of the Q&A part.
Thanks, Reinhard, and thanks, Jose. Excellent presentation. Very exciting, very exciting. Thank you so much. There is a bunch of questions, very, very challenging questions. I'm joking, but really, I think there is good interaction in the chat window. It has been scrolling really fast for me. I'm going top to bottom. First question, Jose is asking. Jose is asking about the general nature of generalization of unseen networks in GNN. I think you handled this in one of your slides. I think RouteNet is specifically related to that, but could you please answer that question, which is asking When you change the underlying graph, the GNN eigenfunctions change as well. How can your GNNs generalize to unseen networks? Jose, you're muted.
Okay, sorry. Okay, so I'm checking the question. Well, I will try to answer this using this slide. So the main idea behind the graph neural networks is that they understand and learn the graph structure information. So you can see this like a distributed system in, for example, in networks. So people from networking, I think they understand when I talk about distributed protocols or distributed system. So the idea is that they combine information between adjacent nodes. So those nodes that are related somehow in the graph. So just receiving information from the neighbors, if you make some iterations, you can receive firstly information from your first degree neighbors, then from your second degree neighbors, and so on. So at the end, these neural networks are specifically tailored to understand how to model all this information. And they create a generic function that enables to model these relationships. So every node in your graph will have the same function, and the graph neural network learns this function. So how to receive or to process the information that you receive from your neighbor, how to combine this with your own state or information, and how to produce a new representation. And this is made for some steps until the process converges. So this is similar to convolutional neural networks. Basically, you are exploiting the structure of your data, which is in the form of a graph.
Thanks, Jose.
I hope this answered the questions.
Yes, of course. I think you have put your mailing list in here. You can expect a lot of follow-up in there, I'm sure. Let us try to cover as much as we can in the chat window. It is still scrolling. So I think the second question which I see here is also from Moshe. He's asking, I've read that operational backward and forward pass operations take order of n squared, whereas traditional CNNs is only order of n. Why do you state that GNNs are faster? Do you want to take it quickly?
Well, in general, all machine learning solutions are much more faster. So you can also execute them in GPUs, in graphical processors. So in the end, I think that using this kind of GPUs, you can reduce, for example, from our experience with not so large networks, with simulation, you can take up to 10 minutes with networks that are probably like 50 nodes or something like that. So they are not very large networks. But then if you process the same data and make the same predictions with, for example, with RouteNet, that we made some evaluations, this can be done in the scale of milliseconds. So probably this is the most important part that enables to perform real-time network optimization compared to, for example, to network simulation tools.
Thanks, Jose. Now that you are in this topic of time, right? I want to slip in my own question. I intend to download your data set and do some experiments with it myself. I mean, I don't intend to win, but it looks very exciting. So what is your typical training time, and how big is your data set?
Well, I should check specifically for this challenge. I'm not sure because we have released many data sets before. So they are in the order of a few gigabytes. And particularly for this challenge, we try to not to make them so large. But I cannot say the precise data now, but if you access to the link of the dataset, which is this link here, you can see the size of the files.
And what is the typical training time that you have seen? I mean, with your configuration.
Well, this is a tricky question because when you are working with neural networks, for example, if you want to make some early evaluations to see if this is a good or not candidate solution, you can make it probably in some few hours, or even sometimes in half an hour, 1 hour, you can see more or less how it will how will be the results. But then if you want to polish and to make a very good solution, particularly for this challenge, for example, you can need some more hours, because the model will evolve slightly in the last part of the training. So this is like an inverse exponential process, where at the beginning it learns very fast, and then it learns quite more slowly.
Thanks, Jose. I will try with my laptop. I have my colleague from South Africa, Fizehe, is asking, networks are also based on regulatory and standards guidelines. How do you build that in the GNN? I think in this particular case, you, Jose, are focused more upon the particular problem of predicting these KPIs that you mentioned, but do you have any quick answers other than that?
Well, the main, as you told, the output of the model is to make these predictions. But mainly, or the main difference, for example, with respect to the baseline model, is that we also included different queue scheduling policies. So I gave here some guidelines that I think they can be very useful for participants, that let's say we recommend to incorporate queue scheduling policies within this graph neural network architecture.
Thanks. I think this is where I had my own question as well. Do we really need to do the participants? Do they really need to do the tuning of hyperparameters, or is that optional?
Well, let's say different approaches can lead to an improvement in performance. Of course, for example, I highly recommend to do normalization of the data. Probably this is a must in general in all neural network solutions. So in the baseline model, we don't make any kind of normalization, and this can lead to many issues when you are training your model. So for example, normalization is very important. Hyperparameter tuning, depending on what parameters, maybe it's not so important.